Let us consider the animation of the water vessels once again. In the first case, you will see that the difference in water level initially in between the two vessels is quite significant. Now, when they are connected, a greater amount of water will flow. Why is this happening? If you recall what I had mentioned in our previous lecture, you will remember that this vessel has a capability to do work in order to transfer the water from this end, that is this vessel, to the other vessel. So what can we say? We can say that more the difference in water levels, greater will be the potential of this vessel to transfer the water to the other vessel. You will notice that the moment the pipes is connected, water rushes in from the first vessel to the second vessel. Similarly, if we consider the second case where the difference in water level was not as much as that in the first case, you will find that a very less amount of water flows from the first vessel to the second vessel. Because in this case, the capability or the potential of the first vessel to do work on water is less as that in the first case, where the potential of the first vessel to do work on the water was more. Lastly, if we consider two vessels which have the same level of water, we will find that after connecting, no water flows in between the two vessels. So we can say that these vessels have no potential to transfer the water in between them because both are at the same level. So we saw that greater the level, that is greater the difference in levels in between the two vessels, greater was the potential to transfer the water. And as we decreased the difference in between the two water levels, the potential to do work on the water, that is the potential to transfer the water, became less. In a similar manner, we can say the same thing about electricity and current. Now, in the case of the water vessels, we saw that more the amount of water in the first vessel, more was the water flowing from the first vessel to the second vessel. Similarly, if we consider potential, and if we say that the potential at a point is greater, we can say that this will be directly proportional to the current flowing through that point. Or in other words, we can say that voltage is directly proportional to current. This proportionality relation holds only under certain conditions. That is, when the temperature remains constant along with all other physical conditions. Now let's see how we can convert this relation of proportionality into a relation of equality. In order to convert it into an equality relation, we have used a proportionality constant. The proportionality constant R is also known as resistance. So now we get the equation as V equals I into R, where R is the resistance. This is the numerical statement of what is known as the Ohm's law. Over here, V, which is the potential, is measured in volt, and I, which is the current, is measured in ampere. R, which is resistance, is measured in ohm, which is given by the symbol omega. So let us see what the significance of Ohm's law is and what it states. We find that Ohm's law is V equals IR, and it states that the current flowing in a conductor is directly proportional to the potential difference across its ends, provided the physical conditions and the temperature of the conductor remains constant. So it is always important to remember that the physical conditions and the temperature of where the conductor has been kept should be constant. Now if I rearrange the equation for Ohm's law, which was V equals I into R, and I bring R to the denominator by cross multiplying, I get I equals V by R. Now if I keep R constant, and I increase V, it means that the current will increase. Similarly, if I decrease V, it means that the current will decrease. And this is exactly what I had stated earlier, that voltage is directly proportional to current. Now, first consider this animation. In this animation, you will find that a very fat man is sleeping on a pipe. Due to this, the structure of the pipe has become deformed. Now you will notice that the man in the middle is trying to get into the pipe because he has to clean the pipe, and his friend is pushing him in, trying to help him through the pipe. But because of the fat man, he is unable to cross from one end of the pipe to the other. So we can say that the fat man is offering a great amount of resistance to the path of the man in the middle, such that his friend is also not able to push him in. Similarly, if we consider a thin man who's sleeping on the pipe, we will find that there is no deformity that has taken place in the pipe. And the man who wants to clean the pipe is able to move from one end to the other quite easily when his friend gives him the original push from this end. So likewise, we can say that if the resistance is more, then a great amount of potential will have to be applied in order to push the current from one end to the other. On the other hand, if the resistance is less, then a little amount of voltage or potential difference will be able to transfer current from one end to the other end. So now we consider the simulation whereby we can verify Ohm's law. Now in this simulation, we consider voltage and resistance, which we will vary, and we will simultaneously find out how the value of current is getting varied. Now if you notice, initially we have considered a voltage of 4.5 volts, we have considered a resistance of 550 ohms, and it has given us a current of 8.2 milliampere. Now keeping the resistance constant, we are going to increase the value of voltage. If you recall, the value of current I is equal to V upon R. So in this case, we are keeping R constant and increasing the value of V. So let's say I increase the value of V to 6 volts. As you can see, the current has increased along with it. That is, earlier it was 8.2 milliamperes, now it has become 10.9 milliamperes. If I further increase the value of V, you will find that the value of current is increasing simultaneously along with V. Now, I want to find out what the effect of the change in resistance is if I keep the voltage constant. So let's say I keep the voltage constant and fix it at 7 volts. The current that is flowing through is 12.7 milliamps. Now I change the value of resistance. If you recall that I is equal to V upon R, so for a fixed V, if I increase the value of R, obviously the value of current will decrease. So it has decreased to 9.9 milliampere when I increase the resistance from 550 ohms to 710 ohms. If I increase the value of resistance further, you will find that the value of current decreases further. Now what happens if I decrease the value of resistance? Let's say I bring down the value of resistance to a value of 400 ohms. The current becomes 17.5 milliamperes. Now if I am to go back to our original value of voltage, that was a value of 4.5. We had found out earlier that for 4.5 volts at resistance 550 ohms, we had obtained a current of 8.2 milliamperes. Now the same condition of voltage, 4.5 volts, we are getting a current of 11.3 milliamperes when I am decreasing the resistance. So thus, this proves that Ohm's law can be verified through such a circuit arrangement. That is, voltage is directly proportional to the current. So now we are going to move forward and find out how we can calculate voltage, current or resistance provided one of them has been provided to us. Now you must be wondering that the relation V equals IR, or the fact that V is directly proportional to current, you might be wondering that what will happen if you forget this relation. Well, you do not need to worry, because this triangle will ease out things for you. Now if you notice closely, V has been kept at the top, I and R have been kept at the bottom. Now how do you find out a particular value in this if the other two values are given to you? So let us say that I and R have been given to you. and you have to find out the value of V. So you simply cover that portion with your hand, and the resulting expression that you get gives you the expression which you need to find out that covered value. So let us take a quick example. Over here, we have been said that we have a 20 ohm resistor and a current of 2 amperes is flowing through it. And we have been asked to find out the voltage across the resistor. Now, if you recall, we can find this out if we cover the value that is required. So in this case, the value that is required is V, so we cover V. Now, if you observe closely, the expression that we are getting is I into R. So simply multiply the value of I and R. That is 20 into 2, which gives us 40 volts. So 40 volts is the answer. Let us take another example. In this example, we have been asked to find out the current, and the information that we have been provided is a resistor of 12 ohms has been taken, 12 ohms, and the voltage that has been supplied across the resistor is 360 volts. So R for us is 12 ohms and the voltage is 360 volts. So R and V have been provided to us. So how can we find out current? We simply cover this value which we have to find out. You can see that the resulting expression is V upon R, and we have been supplied the values of both V and R. So we simply divide the value of V by that of R, that is 360 upon 12, and we get a result of 30 amperes, which is the current flowing through the resistor. So taking a quick recap, we learnt about Ohm's law. Ohm's law states that voltage is directly proportional to current, and we can equate voltage and current if we consider a constant of proportionality. This constant of proportionality, or R, is known as the resistance of the conductor. So V was given as I into R. In other words, we can rearrange this equation to write I equals V by R. So for a fixed resistance, if we increased voltage, we found that current increased. And if we decreased voltage, we found that current simultaneously decreased along with it.